So first thing to do is set the right-hand sides equal to 0. When you set the dx/dt equation equal to 0, you are essentially finding the x nullcline. When you set the dy/dt equation equal to 0, you're essentially finding the y nullcline. It's probably easiest to think about that in terms of y as a function of x in each case. So for the first equation, if you solve that for y, you get y is x squared minus a. That's the x nullcline. That'll be a parabola opening upward with y-intercept at negative a. And looking at the dy/dt equation, solving for y, you get y equals negative x squared plus a. That'll be the y nullcline. It's the reflection of the x nullcline across the horizontal axis, a parabola opening downward with the y-intercept at positive a. As far as finding the actual equilibrium points, it's where x and y nullclines cross. So set these two things equal to each other. Set x squared minus a equal to negative x squared plus a and solve for x. Add x squared to both sides. Add a to both sides. And you get 2x squared equals 2a. Divide both sides by 2. X squared is a. Take the plus or minus square root of both sides. The x coordinates of equilibrium points are at plus or minus square root of a. To find the y coordinate, plug those back into either equation and you get y equals 0. Right? Square that, you'll get a. A minus a is 0, also negative a plus a is 0. So your equilibrium points, the xy coordinates are plus or minus square root of a, comma 0. They are on the x-axis. When a is 1, that's plus or minus 1, comma 0. Let's try to draw the phase portrait. I could say a is 1, but really, perhaps the phase portrait looks basically the same for any positive value of a. The location of the equilibrium points is going to change clearly as a increases. They will move further away from the origin. Does that make sense? Because that's going to get further away from 0 as a increases. But maybe the picture basically looks the same. Let's see if it seems reasonable to assume such a thing, at least. If a is positive, what does the phase plane look like? Draw the nullclines to help you. The x nullcline, remember, was y equals x squared minus a parabola opening upward. Y-intercept at negative a. So the x nullcline looks about like this. It's an x nullcline, so you got to cross that with 0 dx dt, 0 first component of velocity vectors in the vector field. You got to cross it vertically. Make a bunch of little vertical lines. It's not a straight line solution. It's not even straight. It's not a curved solution. It's not a solution at all. It's just showing you how the solution curves cross that line. The y nullcline is the reflection of that across the horizontal axis. Downward pointing parabola. About like this. And yeah, where they intersect by symmetry, it's got to be on the x-axis. You're going to cross that horizontally. And where x and y nullclines touch, that's equilibrium points here and here. I saw many of you got this far, but then the hardest part is drawing the phase portrait after that point. Think about the signs of these things, the right-hand sides, in how many different regions? The regions in the plane separated by these nullclines. Well, there's one up here, there's one in here, there's one down here, one over here, one over here. 5 regions to think about signs of dx dt and dy dt. Actually, you can focus on each one individually. Again, the red one is the x nullcline. It's the vector field is 0 along there. think about this. Is that positive above that red parabola or negative? When A is positive, you could try a test point like the origin for one thing. You could try. Plug in X is 0, Y is 0, you just get A. And A is positive, so that's positive. When you're above this red curve, solutions have to be going to the right. dx/dt has to be positive. So they're rightward pointing in this region and also rightward pointing in this region. Those are both above the red curve. Downward pointing below the red curve. Down here, over here. Excuse me, leftward pointing below the red curve. We're focused on dx/dt. So we need to think about, do solutions go right or left? dy/dt. Think about the sign, positive or negative of that. Again, you could plug in the origin as a test point. Plug in X is 0, Y is 0, you get 0 minus A is negative A. And if A is positive, that's negative. So at the origin, dy/dt is negative. When you're below the blue curve, dy/dt is negative. And when you're above the blue curve, dy/dt is positive. Now try to draw solutions, the very hardest part. Pick sort of like a random initial condition. Oh, I don't know, maybe in here to start with. These arrows indicate you've got to go to this direction, to the southeast. How far will it go? That's hard to say, but it will cross the X nullcline somewhere. Okay, I've drawn that one to make it look like it's going to cross on the y-axis, but maybe it goes over here. And then you got to go to the southwest and you go out this way, and probably at some point you're going to cross the blue parabola again. If we started closer to this equilibrium point, maybe it's more clearly crosses the blue parabola right about here. Then you're going to the northwest. It can't possibly cross the red parabola again, right? Because if it did, it would have to at some point. Well, excuse me, I guess it could. Never mind, I said that wrong. If it was close enough here, certainly it's going to cross the red parabola like that before going to the northeast. There, it can't possibly cross the red parabola over here, because if it did, it would have to be going to the southeast there, and it can't. It's got to continue going to the northeast here. Pick some other initial conditions, maybe one over here. Symmetry probably is going to come into play. I'm not doing a very good job here. Cross that horizontally. Oh, no, I'm doing a really bad job. Sorry. Ignore that. Easy to make a mistake. Go to the northwest here before crossing. Then you're going to the southwest. Ignore this. Here you'd cross this way before going to the northeast. It should make some intuitive sense by continuity. There's got to be some solution curve that heads straight toward that point. Maybe not actually on a straight line. I know I said the word straight, but it doesn't necessarily have to be a straight line. It's probably not. Guess symmetry is not coming into play as much as I was initially thinking here. Drawing in some other solutions here. There's got to be one that's going toward the equilibrium point this way. You start to get a little feel for what's going on. It looks like this point right here. Look at it with me here. That looks like some sort of spiral source, doesn't it? And this point looks like some sort of saddle point. But how do you know? Is there a way to know for sure this is a spiral source and this is a saddle point? There actually is. That's called linearization. where you try to get rid of nonlinear terms essentially in the differential equations on the right-hand sides. However, I said get rid of nonlinear terms with the caveat that you only do that in the most obvious way, like deleting those x squared terms, when your equilibrium point is at the origin. Our equilibrium points are not the origin. Unless a is 0, then they merge. That's why a is 0 is a bifurcation value. As a approaches 0, these two equilibria merge into one equilibrium point at the origin, and then when a is negative, they have annihilated each other. There's no equilibrium points when a is negative. Yes, we want to throw away nonlinear terms, but if the equilibrium points are not at the origin, that's tricky. There's two ways to approach it. The book talks about both methods. I also talk about both methods in the lectures. The simpler method is to use something called the Jacobian matrix. Jacobian matrix. Anybody in here had multivariable calculus? A few of you in the back, okay, yeah. You probably heard about Jacobian matrices and multivariable calculus. They're showing up here again. The purpose is different. In multivariable calculus, the purpose is to use Jacobian matrices and the determinants to do change of variables, general change of variables for double integrals, triple integrals. Here, the purpose is different. The purpose is to do what's called linearization, to essentially try to approximate this nonlinear system with a linear system near the equilibrium points. I call it J in honor of Jacobi, though other people call it D in honor of derivative. Derivative is not a person's name, but because it is kind of a derivative, it's a matrix whose entries are the partial derivatives of the right-hand side functions with respect to x and y. Upper left entry is the partial of the first component of the vector field, little f. I won't bother with the subscript a. I could. No, okay, maybe I should. With respect to the first variable, you won't always have a parameter there. We do here. Let's have it quiet here, please. This upper right entry is the partial of that first component with respect to the second variable. Again, the a is just the parameter here. I was tempted to not include it at first, but I'm including it. Lower left is the partial of the second component of the vector field with respect to the first variable, and lower right is the partial derivative of the second component with respect to the second variable. This is called partial derivative notation. These curvy things are essentially fancy D's. The only reason to use a fancy D in this context is just to emphasize mentally, oh, my functions depend on more than one variable, and so that's just sort of a way to remind yourself of that. You could use ordinary D's. Don't read too deeply into this. It's just a convention. It gets even extra strange in some physics classes because sometimes you'll use deltas instead of D's, and it's like weird. Why are you using deltas sometimes and D's other times and stuff? It's confusing, right? It's just not a big deal. Don't worry about it. It's confusing because different people have different preferences with those things. Okay, so how do you take partial derivatives? You just treat, with respect to x, you just treat y as a constant. And of course, a is a constant. So you differentiate this with respect to x, you're just going to get negative 2x. Differentiate it with respect to y, you just get 1. Negative 2x and 1. Right? Differentiate this with respect to x, treat the y and a as constants. It's negative 2x. Differentiate it with respect to y, you get 1. Something kind of similar happens with this one, except the derivative with respect to x is positive 2x. There's your general Jacobian matrix. It's a function. A matrix valued function. Plug in a point x, y, you get a matrix. Weird. Well, We do lots of weird things in this class, but there it is. What do you want to do with it? You want to plug in the equilibrium points into it. J of square root of a comma 0 is what? Replace x with square root of a, replace y with 0. Well, there are no y's, so you don't have to worry about that. There's the Jacobian matrix evaluated at the right equilibrium point. If I evaluate it at the left equilibrium point, plug in negative square root of a, I get positive 2 root a. The negative sign just switches where it is, which you might not think is a big deal. You know, is it really a big difference between these two matrices, just switching the negative sign? It actually does make a big difference. These are two matrices, and if A is constant, they are constant matrices. And I could think about the linear system for these matrices. I could think about eigenvalues and eigenvectors. I could think about phase planes where these are the matrices for my system. And if I'm trying to think about such systems as quickly as possible, the quickest method is to think about the trace determinant plane to identify the nature of the equilibrium point at the origin of these systems. At the origin? But wait a minute. The origin is not an equilibrium point. Yeah, it's not an equilibrium point for the nonlinear system, but I could think about the origin being the equilibrium point for systems corresponding to these matrices. And the idea, the big idea here is those systems, which are linear systems, where eigenvalues and eigenvectors are relevant, tell you the nature of the equilibrium points for the nonlinear systems. We should get this one to be a saddle point and this one to be a spiral source. The trace determinant plane is the quickest way to see that. This matrix has a trace of negative 2 root a plus 1 and a determinant of, looks like it would be minus 4 root a. Right, double check that in your head. This one has a trace of plus 2 root a plus 1 and a determinant of positive 4 root a. Think about the trace determinant plane. For this one, no matter what a is, as long as it's positive, so you're not taking a square root of a negative number, no imaginary numbers here. The determinant is negative, you're down here somewhere. Meaning, for the linear system corresponding to this matrix, the origin is going to be a saddle point. Right? That's where saddle points occur. When your trace and determinant, when your determinant is negative, you have a saddle point at the origin. Just like this seems to be a saddle point. On the other hand, with this one, the determinant is positive and the trace is positive. You're up here. For sure, it's a source. Is it a spiral source or a real source? Seems to be a spiral source, but maybe looks could be deceiving. Is there a way to know for sure? You could think about where the repeated root parabola is here and try to figure out, are we above or below that repeated root parabola? Again, that had equation d equals t squared over 4, which is equivalent to 4d equals t squared. If I calculate t squared and I also calculate 4d, am I going to be above or below the parabola? Is it going to be clear that one of these is bigger than the other? It's not clear to me. 4d is 16 square root of a. What about t squared? Square that thing, I'll get 4 square root of a. No, excuse me. 4a plus 4 square root of a plus 1. Maybe the answer depends on a. If a is 1, let's assume we're in the case where a is 1. This becomes a 16 and this becomes a what? 9? t squared, 4d is bigger than t squared. D is bigger than t squared over 4. You're above the repeated root parabola spiral source when a is 1 at least. 4d is bigger than t squared means d will be bigger than t squared over 4. You'll be above that curve. Just like it looks like a spiral source. Technically speaking, what's going on here in justifying all this is something called the Hartman-Grobman theorem, which I do talk about in the lectures. It's a very, very advanced theorem. Very difficult to prove. We do not prove it in any, we do not even come close to proving it. We don't even really fully use it. We just sort of talk about it to get a little intuitive feel for what it means to justify such a thing. The fact that we're not on the positive d axis is actually important. Although, in fact, if a is 0, then okay, never mind. If a is 0, the determinant's 0, and the origin's kind of a degenerate equilibrium point. Don't worry about it. Okay. What happens when a is 0? Let's just try to get a little feel. I'm not going to do a full analysis here. As a increases towards 0 or decreases towards 0, so I'm imagining a decreasing here, these parabolas are going to merge. Well, they don't literally merge. They move together, so to speak, so that these points move toward the origin. The red one becomes this one when a is 0, and the blue one becomes this one. You've got one equilibrium point at the origin. Still cross the red one vertically and the blue one horizontally. Do I want to bother? Let's not bother doing this by hand anymore because I want to do something else. Well, let's quickly look and see what Mathematica produces. So here's Mathematica stream plot when a is 1. But I want to see what happens as a changes here. I could put this inside and manipulate. And change this 1 to an a. And let's actually let a decrease. So I'll start with a to be, say, 4 and go down to -4. That'll make a decrease. Those equilibrium points are on the wrong spot, though, then. Let's see here. Square root of a. Oops. Square root of a and negative square root of a. So watch what happens as a decreases. So here a is 4, 2 equilibrium points. A bigger value of a, I'm looking at this left one, it looks like maybe it's more likely to be a non-spiral source there, if a is big enough. As a decreases towards 0, like when it's 1, does it more clearly become a spiral source? It's looking more and more like a spiral source. When a is 0, the equilibrium points have merged. What kind of behavior is it near the equilibrium point at the origin? It's kind of weird, actually. It's like it's half of a spiral source and half a saddle. Isn't that weird? Is that really what's going on? Yeah, it actually is. It's called a degenerate equilibrium point in that case, and linearization doesn't work anymore. When a is negative, then, why is it going backwards then? When a is negative, there's no more equilibrium points. So bifurcation has occurred. It's like the equilibrium points are matter and antimatter. They've come together, they've annihilated each other. Is that really an application? No, it's just for fun. Okay. is just pretend.